So I'd like to continue our discussion of compensation in this third lecture. We observed that the pole spread requirement makes that compensation capacitor requirements too large. So what we're going to do is look at the concept of Miller compensation in an attempt to reduce the size of that capacitor. But before we do that, I've got a couple questions to ask. What about just making C sub C larger than what is needed? So we're guaranteed to satisfy the pole spread criteria.
So my question is, does the compensation capacitor move one pole or move both?
We'll look at expressions for that. Oftentimes it moves one, or it does what's called pole splitting. It moves one up a little bit higher and one down a little bit lower. It depends on the structure. But it dominantly moves one. So what about just making C sub C large? That makes your life easy.
Intuition tells me that would be bad for the bandwidth of our device.
It's bad for the bandwidth and it's bad for energy efficiency. So that's not a good solution. GB will degrade, power and area will increase. What about providing additional compensation by making CL larger? So we know that putting a large capacitor on the internal node is good. We know putting a large capacitor on the output node is good. So let's be double good. And let's put some more capacitor on both nodes. Is that a good solution? Okay, so it might degrade GB a little bit, and the power. Good observation. Anything else?
Phase margin.
It'll make it better or worse.
Not sure. I don't have that.
It was capacitor. You lose whatever phase you use for capacitor.
You what?
You lose whatever phase equal to the capacitance of those capacitors.
So it'll make the phase worse. What you're saying?
I say if they're either parallel or in series, they will be equivalent to one capacitor.
Yeah, I understand. So we're going to put more capacitance on here. Put an extra capacitor on here.
It won't change the phase model.
Okay. So it makes the area a little bit bigger. Power might go up a little bit, but outside that, we're all right. It doesn't change it or makes it better. We're going to put it on to make it better. Remember, putting capacitor on either node helps it. Jay. So let's draw a picture of what happens here. So we've got P1 here. And we're going to assume this is due to C sub C. We've got P2 here, and this is due to CL, right? So we went to the effort to put some C sub C in to get P1 where we wanted it. And now we say we're going to make these even better. We're going to even add some additional capacitance CL. Garrett, you're grinning. What's going to happen? Right, so you put some more CL on, and it won't affect this pole. What will it do to this pole? Move which way? This way. Move it over here. What did you do to the pole spread?
You decreased it.
You decreased it. So you make it worse. So it's even worse than the power issue. You will decrease your phase margin. If you put very much on there, you will maybe even oscillate. Okay. So more is not better. Poles will move together and degrade performance. What about compensating for a worst case beta equals 1 so we can forget about the beta dependence? Power efficiency. If you compensate for beta equals 1 and you only need to work for beta of 0.1, you're going to have way more power spent than you need. It'll certainly work great for beta of 0.1, but at the expense of too much area and too much power. Okay. So the bottom line is there's not a good way to get around compensation. Anything you do besides try to put the pole where it's optimal is going to degrade the performance. It is a good solution for catalog parts, but only because the industry is willing to buy op amps that are overcompensated and burn more power than they really need to burn. But there's always a penalty in GB and power and area if you overcompensate the amplifier.
But we want our batteries to last longer nowadays, right? For our
What?
cell phones. Wouldn't you say we're maybe starting to move away for our catalog op amps and our battery-powered devices? That's starting to become more of an issue.
Right. So what will happen is so right now if you look at op amps, let's assume that I don't know what percent. Let's assume 90% are compensated for beta equals 1. And if you realize that we're going to have applications that have beta of 0.5 and beta of 0.1 and beta of 0.05 and beta of 0.01, then you can say, well, look at this opportunity. We've got 4,000 catalog op amps now that are compensated for beta equals 1. I want another 4,000 op amps compensated for beta of 0.5. And another 4,000 op amps compensated for beta of 0.1. Would you be able to build better systems? Absolutely yes. The op amp industry may be forced to do it if one of these companies came out and came with a host of catalog parts, they're compensated for their guys' beta. Because then they would start putting their parts in sockets that would give better system performance than the other catalog parts. But until one of the major players does that, we'll probably still live with burning more power than we need. So you might have there might be a business plan there that said, hey, it might be a business plan, but if you started getting much business, you can imagine the big boys would be there to compete with you in a hurry. And all they have to do to bring their parts in usually would probably be to change a compensation capacitor, and then they would have a part that had be more power efficient. Does that make sense?
Absolutely, yeah.
Well, we talked about the large number of structures that we can work with. Example, sketch a circuit of a two-stage internally compensated op amp with a telescopic cascode first stage, a single-ended output, tail current bias first stage, tail voltage bias second stage, P-channel inputs and N-channel inputs on the P-channel inputs on the first stage and N-channel inputs on the second stage. Okay? So we've described this op amp that's outlined in these green boxes here. One of these 2,000 some op amps. Architecture is pretty easy. Telescopic cascode first stage with P-channel inputs with a current mirror bias. Tail voltage bias on the second stage with N-channel inputs. Compensation capacitor on the internal node. We're done. Okay? Yes?
When we're doing this method for compensation capacitors, are we tying it to VSS all the time?
You can tie it to any DC node in the circuit you choose. You can show that if you look at small signal analysis, compensation is dependent upon small signal analysis, assuming it's linear. You can show that VDD and VSS, and if there's a separate ground, they're all the same potential in the small signal circuit. So it makes no difference which place you connect it. Good question. Does that make sense? How'd that get in here? Oh, this is the first commercial op amp. It was by Philbrick. And it had about a 20-year run. Is that a good run for a part? Yeah, 20-year run. Shockley and Noyce and Kilby were a disaster to this business. Because as soon as they invented the IC and guys like Whittler figured out how to build op amps, they quickly killed the market for this part. But for 2 decades, this was king.
Those are
Two-
weird looking transistors.
What?
Those are weird looking transistors.
They are, aren't they? They are, aren't they? So if you look at 2 decades, that's close to the engineering career of a lot of engineers. For a whole career, for nearly a whole career, people were using this to build op amps. Now, I mentioned I used to work in the filters area. At the time that people were building filters, active filters, they used op amps. Op amp designs of the 50s and 60s were typically ones that said you can use one op amp in your design and have as complicated of a RC or RLC network as you want, but don't use more than one op amp in your design. I'm only slightly exaggerating. Why do you think that was the case? What? They were expensive. You needed active devices, but boy, if you use more than one, the cost of your filters would be really high. It really constrained the people who were building filters at the time. Here's one of the bad guys that helped put the guys out of business. This is Whittler. Many people say that Whittler started the field of analog IC design, and he's considered a brilliant engineer. And if you go read stories about Whittler, he's a very colorful character, and he was brilliant. A lot of the designs that came out in the industry in the 60s and 70s were due to Whittler. He began his career at Fairchild, where he designed a couple of the original op amps. By 1966, the commercial success of his design became apparent, and Whittler went and asked for a raise. He was turned down, and he immediately went to National Semiconductor, who was just getting started at the time. At National, he continued to turn out amazing designs. His goal was to retire at a young age. He retired at 30. Although he retired, I think he spent a lot of time in Mexico after that. He found some place in Mexico that he really liked to live. But he still couldn't get the IC design challenge out of his mind, so he still popped up every once in a while with a new design, working as a consultant occasionally. But I don't think he had to. It was because he wanted to. Oh, here's another guy. Now, he didn't always look like this. This is Fullagar. And at the time that National was putting out op amps, they had project numbers. Project 701, Project 702, Project 703, Project 741. He happened to be on Project 741. And they named their op amps by the project numbers. So there's 702 op amps, 703 op amps. I think everything before 741 was externally compensated. So he designed the first internally compensated op amp on project number 741. He was 26 years old when this was designed. He had no op amp design experience. He was almost a fresh out. They said, design an op amp, and we'd like to see if we can get rid of that capacity. Introduced in 1968. It was the largest selling integrated circuit ever. You can still buy it. Still sell a lot of them. Still in high volume production, even though it's over 40 years old. He also started the linear design activities at Intersil. Intersil was a major linear company back in the 70s. And he was a co-founder and the catalyst behind Maxim. Okay. So how old were some of these guys when they did brilliant things? Not old. Kilby was about, yeah, you're just about right. So be careful with making any assumptions that you're not to the point where you make similar contributions. Because a lot of the big breakthroughs came from people that were between 25 and 35. Kilby, Noyce, Whittler, Fullagar, a whole bunch of others. Make sense? Pardon?
Need the young minds. We're still fresh in the world.
That's a good observation. I think there's a lot to it. And you also haven't been tainted to not look at things a certain way. You might say, can I try something? and you don't get people say, you can't do it. You just go and do it. So let's look at analysis of these structures now. I'm going to try to do this as much as possible by inspection. Occasionally I'll write a couple of equations and I'll solve a couple of equations in the background and give you the solution. But I want to do as much as possible by inspection. Why do I want to do it by inspection? If I can do it by inspection, we'll get insight in what we're trying to do to get certain characteristics. And hopefully you can use that thought process if you want to work on different structures. Make sense? So our goal is to try to do as much as possible almost by inspection. So, if you have an internally compensated op amp, and we have no zeros present, then we have two poles. I'm assuming that P1 is the dominant pole, the lowest frequency pole, and P2 is the higher frequency pole. Of course, the bandwidth is P1. So I want to analyze the internally compensated two-stage op amp. I can put in a model for the first stage. This is the quarter circuit, the counterpart circuit. Put in a model for the second stage, the quarter circuit, the counterpart circuit. Put on the compensation capacitor, and I've got a circuit I can analyze. If I look at the number of nodes I've got to consider here, it's pretty small. If you go back to the structure, I really have two nodes. The node at the output of the first stage and the node at the output of the second stage. So if I apply Kirchhoff's current law at those two nodes, I have two equations and one extra unknown, the V1 that I can eliminate. I can actually write down most of this by inspection, though. I can solve those early equations, but let's try to do it by inspection. So if I go back and look at this structure, the DC gain is going to be the gain of the first stage. You put a DC is in times the gain of the second stage. The gain of the first stage. Should we write out what the gain of the first stage is in terms of the GMs and the G outs of those blocks? Okay, so what's A1? A1, 0 DC is equal to what? GM1 or G out 1 plus G out 2. What's the A01? What's A02? GM2? Or maybe I should call it 3. GM3 over G out 3 plus G out 4.
I thought that the equivalent G out of like a diode connected would be GM plus G out. So would it be like GM2 plus G out 2? Or no, I guess it's grounded. Yeah, never mind.
Okay.
P1 and P2 are totally different. It's not a.
Yeah, it's not diode. It's like, yeah.
So I've got the gain. Dominant poles on the first node. So what's the bandwidth?
G out 1 plus G out 2.
Over CC. So the bandwidth is equal to G out 1 plus G out 2 over C sub C. Gain bandwidth product. This times this times this. How about the second pole? P1 is the dominant pole. Can we get the pole? No, give it to me. It's the capacitor times the space in the node. So it's 1 over C sub C. Well, I guess G out 1 plus G out 2 over C sub C. That's the first one. How about the second pole? P2.
G out 3 plus G out 4.
G out 4 over C out.
Over CL. Fantastic. What more do we want? We have the poles, we have the DC gain, there's no zeros, then we're done. Okay?
Excuse me,
Yes.
when doing the pole two, when we open circuit C1, we still have something from the first two transistors coming up, right? Like in the example we saw before, with the two capacitors.
I didn't quite understand.
So while determining the poles for the capacitor marked CC,
Yes.
we need to consider the first stage things too, right? Because
Okay, so what we do is we want to look at the pole on this node.
yes,
So we let all low frequency poles or capacitors be short circuits. So this goes to an AC ground. If this goes to an AC ground, all we see looking in here is this output conductance and this output conductance. Okay?
So which one we determined to be the high frequency and the one is low frequency?
We've assumed that it was internally compensated. So the capacitor C1 in the previous analysis was a big capacitor. That's the low frequency pole. How about this structure here?
It's the same. Since
Same poles there. Now we can do Kirchhoff's current law at the nodes. So here I've analyzed the structure, and it doesn't make a difference whether I call this I call this externally compensated, and we see the same expression we had before. So let's assume now that I want to compensate the circuit so that the pole spread, P2 over P1, is kind of in the middle between 4 beta A naught and 2 beta A naught. So I'm going to compensate it for 3 beta A naught. So I want to make this pole ratio equal 3 beta A naught. So if I plug in P1 and P2, then I want 3 beta A naught, this was A naught, has to be equal to P1 over P2. And then I can solve the equation for C sub C, because that's what I need to do the compensation. So if I solve this equation for C sub C, C sub 3 is approximately 3 beta times CL times this term here. Since the pole ratio has to be very large, this compensation capacitor, these are GM over G outs, these are gains, right? So C sub C gets real big. Not a problem if it's external, but internal it's a problem. So let's address that issue. Now, I would love to talk to Fullagar or read how he had his insight into it. He didn't do it in one day. But this is such a simple concept. So let's look at it. This is the Miller capacitance concept. If V2 is equal to minus A V1, and A is large, then if you look into the circuit from the right here, C1 equivalent is approximately equal to the bridging capacitor C times A. And if you look back into the circuit from the right side, the equivalent capacitance here is about C. So it says that you can replace one bridging capacitor C by 2 shunt capacitors, one that's value AC, A is the gain and C is that capacitor, and the other is value C. Okay. Does everyone remember the Miller effect?
From 330? No.
We didn't talk about 330. 230 you may have talked about it. Or
I'm
201.
not sure if they go over it still at 230.
What?
I'm not sure if they go over it at 230.
We identify the Miller integrator, in other words, that first order low pass filter.
Yeah, we call it the Miller integrator, but I don't think we do. By the way, this is called capacitance multiplication. So there's a lot of applications where you want a capacitor that's big, but you don't want to go to the resource to put a big capacitor in. So if you build a circuit where you take this voltage here, so here's a node, and you build an amplifier with a gain minus A. If the input impedance is infinite, you feed that back here, and now what you have is a 1 port. You can show, we'll do it in just a minute, you can show that this is equivalent to a capacitor that's value AC. So that's called a capacitor multiplier. You take a small capacitor and multiply it. We can do the same things with inductors, and we can get inductor multipliers and so forth. Thus, if you have a big gain, a large capacitor can be created with a much smaller capacitor if a capacitor bridges two nodes with a large inverting gain. To give some feel for why that happens, if you take this capacitor here, a regular capacitor, excuse me, if you take a regular capacitor, as the voltage goes up, the current goes up. And there's a certain relationship between the voltage and the current in a capacitor given by the differential equation that carries the capacitor. If you take this structure here, as this voltage goes up, this voltage goes down real fast. And if this voltage goes down, this voltage goes up real fast. So it brings a lot more charge on that capacitor than it did if you just had a capacitor like this. But since it's still a capacitor, it looks like a much bigger capacitor. So here's the two equivalent circuits that we said existed. Unfortunately, if A changes with frequency, this equivalence only applies if A is constant and negative. If A changes with frequency, then it doesn't quite hold. And the impedance you see, instead of being 1 over SC, it'll be a slightly different impedance, maybe. That might still look about like a capacitor at some frequencies, but may start to deviate from looking like a capacitor at different frequencies. So, what I've just described is the concept that most people have for doing Miller compensation. But they will often find that the fact that the gain decreased with frequency starts to limit the effectiveness of this approach. It doesn't anywhere near kill it. It just starts to limit it. So we can still derive a lot of benefit from it, just not quite as good as this analysis suggests. But that's where a computer comes in. Because we will neglect the effect of the gain initially and get close, and then maybe make a few changes in the size of the capacitor that will compensate for the fact that the gain is not constant with frequency. Okay? So it gives insight, but won't give exact results. Here is an analysis that shows that the capacitance multiplication takes place. So we have this amplifier with a gain of minus A, and I can look at this current Ix that flows in here as a function of Vx. And the current Ix is equal to this voltage, which is Vx, minus this voltage, which is minus AVx, times the conductance, which is 1 over SC, which is SC, which I factor out the Vx, it's Vx times S times C times 1 plus A. And so the input impedance we see to that network is simply Vx over Ix. So if you take Vx over Ix from this equation, we get 1 over S C times 1 plus A. And that tells us then that this is equivalent to capacitance of value C times 1 plus A. Okay? So, but if A of S is not constant, then that expression for the input impedance will not quite be 1 over S times something. Make sense? So here's what really happens. An ideal capacitor will have a conductance that increases linear with frequency. 1 over, in this case I have a logarithmic axis. If you look at the Miller capacitor, at low frequencies the gain is constant. So the Miller capacitance, input impedance look like you want. But when you start to get to higher frequencies, the gain of that amplifier starts to drop off, and your magnitude of your conductance will deviate from this line here a little bit. And you'll get some phase shift that's not quite 90 degrees as well. However, as long as the frequency is below this point here, it pretty much looks like a large capacitor. Make sense? So now let's see how we apply Miller compensation. We want to get rid of this big capacitor here, but we still want it to look like it's there. It just happens that the voltage gain from here to here is what? It's big and negative. So what do we need on the other side of the capacitor? A big and a negative gain. So why don't we just take this capacitor here? This is a big negative gain, and that will make an input capacitance look much bigger than this capacitor here. Make sense? And then we'll put an additional capacitor on the output node, but if C sub C is small, it won't affect the overall load capacitance very much at all. So it's kind of a win-win, well, not quite a win-win situation. It slightly lowers the high frequency pole, but it dramatically lowers the low frequency pole. So here's the circuit structure. Now I'm going to try to do an analysis that includes the effect of the frequency degradation of the second stage, because we said it's not quite perfect. So we could assume it's perfect and then do iterations in the computer, or we could try to see if we can include in our analysis the limitations that this frequency-dependent gain of the second stage has. So, common source first stage. Now, I'm showing this as a cascade of 2 stages. It could easily be a differential first stage, and I'll just have a big G and a big GM, so it really doesn't affect the analysis arm at all. So, model for the first stage here, and the output conductance is the load that we see on top. Compensation capacitor bridges the 2 sides here. Looking up here, we see the output conductance G out 2, and down here we have the model of the quarter circuit F2, and the load capacitor CL sitting here. I made no assumptions now in the fact that gain has to be constant. Should we try to get this gain by inspection again? If I want to write Kirchhoff's current laws at 2 nodes, I can do it, and then solve those 2 equations. It's not hard to do. But let's try it by inspection. AV0. Same as before. GM over G out 1 F1 plus G out P1. Capacitors are gone at DC. In the second stage, GM F2 over G out F2 plus G out P2. Now, This is our pole before. Right? Well, this pole is a low frequency pole. So at low frequencies, we can neglect the high frequency pole. So at low frequencies, I can neglect what's happening out here. And this capacitor at low frequencies looks like C sub C times the gain. Right? At low frequencies, this capacitor looks like C sub C times the gain. So P1 then is equal to the P we see on this node, which is G out F1 plus G out P1, times that capacitance we see on that node. And that's Miller capacitance. It's C sub C, and it got multiplied by the gain of the second stage, which was GM_F2 over G out F2 plus G out P2. Okay? So we see that. Okay. Bandwidth, of course, is internally compensated, so the bandwidth is essentially P1. So we've got the bandwidth. I'm almost done. If I get the gain of the two poles, I can write down the transfer function. If it's all pole. In this case, there's a 0 present. Okay, let's get the second pole. To find the second pole, now I'm at high frequencies. At high frequencies, that capacitor C sub C acts like a short circuit. Right? Remember, it's a low frequency capacitor, so it acts like a short circuit. So I'm replacing C sub C by a short circuit. So at high frequencies, I have CL here, and let's see, what do we see? I see G out F2. In parallel with G out P2. Oh. This device has the gate connected around the drain. So this is now a diode connected device. So when I look at this as a 2-port or as a 1-port, I really see GM_F2 plus G out F2. Everybody see this diode connected device here? Okay. So the pole in this node then is going to be 1 over CL times G out F2 plus G out P2 plus GM_F2. You ever see that? Okay. Oh, we're done. We've got. How about the GB? The GB previously was given by this expression. Now the GB well, the bandwidth has certainly changed, and I multiply that by the gain, and I get GM_F1 over C sub C. Does this look different than what we had before? It does. However, this C sub C and this sub C aren't the same. This sub CC has now been changed by a factor of GM_F2 over G out F2 plus G out P1 by the gain of the second stage. So basically the gain balance product is the same. Ben, how are we coming on time?
Got 11 minutes left. Okay.
So, has GB decreased by using Miller compensation? The answer is no. So, this is one of the most widely used op-amp architectures. It's just a cascade of 2 common source stages. The compensation capacitor CC is used to get wide pole separation using the Miller effect. There's 2 poles in this amplifier. Now, one thing this analysis missed, there's a feed-forward path through that compensation capacitor. And we will see that that introduces a right half plane 0. And we can't pick up the zeros by this analysis. Okay, so we aren't quite perfect on this analysis, We will come back later and see how we can. Is it hard to pick that 0 up? So what did I do here? I did it by inspection. And I found the poles and the DC gain. But if there's a 0 present, we're not going to find that 0 because this method only finds the poles. So how much work would it be to find that 0? Not too much. What would I do?
Would you use this most of the model to find the transfer?
Yeah, we already have the model there.
Yeah.
So instead of trying to write down these things by inspection, we'd sum currents those two nodes and eliminate the voltage on the internal node. Make sense? So, not difficult to do it. I haven't done any calculations tonight. Do we know a lot about how these circuits operate already? With no calculations. Don't you feel guilty? What?
I feel like there's still a lot of math going on.
There's not.
Internal.
See some
Yeah.
plus signs and division signs on the board.
Yeah, you're right. I failed. I did write some equations. They weren't too bad though, were they?
No.
So if you look at this structure here, this is now not just using a common source amplifier, but a fully differential stage. We can still do this by inspection as well. If you look at the DC gain, we calculated the DC gain of this stage before and the stage before, so we can write that down by inspection. Finding the pole on this node, this is an AC ground with a differential excitation, so the analysis I did before applies exactly here. The only thing is the GM is going to have a factor of 2 because you have a current mirror connection on top. If I want to look at the pole on this node, the dominant pole, at C sub C, it's 1 over C sub C times GM5 over G out 5 plus G out 6, that's the gain, times the condensation capacitor CC. And the pole on this node, again, Miller effect, this becomes a short circuit. So this device comes diode connected. This becomes a short circuit at high frequencies. So this gate and this drain are tied together. So we look up here and we see a GM5 plus a G out 5. And down here we have a G out 6. So the sum of GM5 plus G out 6 plus G out GM5 plus G out 5 plus G out 6 is the conductance on this node. And we multiply that conductance by the load CL, and that finds out the pole. Yes?
When you're doing that and you're saying that CC becomes a short circuit,
Yes.
why are we not looking at the output G's for the 2 and 4?
Oh, yeah, you got me there. So, let's try once more. You got me there. So, I missed 2 output conductances. So, the P2 should equal 1 over CL, and I said it was GM5 plus G out 5 plus G out, what's the bottom? 6. Francisco pointed out I missed 2, plus G out 4 plus G out 2. Thank you. How do G outs compare to GMs? They're pretty small compared to GMs, unless there's dramatic difference in currents. They're pretty small compared to each other. That's the problem with this stuff. You can make so many mistakes and you can't get the wrong answer. Okay. So I got the right answer for the wrong reason earlier. Now I get the right answer for the right reason. Okay. Thanks for pointing that out. Oh, we just went through this now. We talked our way through this and wrote down the gain, the pole P1, the pole B2, and the GV. The only thing we're missing here is that 0. What?
You say we don't see them? Or you don't need to worry about them or something like that?
Pardon?
When you say like 0 is one big deal, like,
Well, they do affect the frequency response a little bit. They don't affect the stability. When you compensate the structures, you compensate for poles, so feedback poles. So we've got the poles and feedback structure. So this will pretty much allow us to see to it that we've got it between 45 and 90 degrees. But I don't quite have the transfer function right. Does that make sense? Yeah. So right now I look at it as a 2-pole transfer function. There's 1 0 in there as well.
so ideally that will give you a 90 degrees phase margin.
What?
Ideally that will give you a 90 degrees phase margin.
No. The 0 doesn't affect it much at all usually. We'll come back and talk about that 0 later a little bit. Right now we're trying to, and what'd you call that? What'd you call that stuff?
What?
What phase what?
I'm thinking about
Where's
control
phase
and
margin?
systems. Control and systems. Because when you have a 0 in your system, you gain 90 degrees instead of losing 90 degrees.
Yeah. Phase margin.
That's imaginary too.
Dr. Tips, talk about phase margin.
And we can,
Do we need phase margin?
it depends which criteria.
Did we need phase margin to put the poles to avoid overshooter ringing? No. Well, we assume it's all pole system. If it's all pole system, we don't need phase margin. Can you have situations where a phase margin looks good and the system is unstable? Yes. Can you have a situation where the poles are in a good location and the system is unstable?
Yes.
No. If the poles are in the right location, system's always going to be stable, and it's not going to have ringing or anything else going on. Okay. So a lot of people like to talk about phase margin. I'll talk about phase margin also after I talk about poles. I'll probably do it for 2 reasons. Number 1, I don't want you to be non-conversant with other people that are in the industry. But I'm not a big advocate of phase margin.
Why?
Because you can build systems that have phase margin that looks good, they're lousy. You don't build systems that have poles that look good, they're lousy. The good news is, usually we're looking at second order systems. With second order systems, we will look at exactly what the relationship is between phase margin and pole locations.
Yes.
So then you have your choice. I'll work with phase margin and pole locations. Now you go up to a third order system. There is not a nice relationship between the pole locations and the phase margin. We still use phase margin criteria to build higher order systems. And there's where you can get in a little bit of trouble. Does that make sense?
Yes.
So we will talk about phase margin. I'll try to show when there's an exact relationship between pole location and the phase margin, and then you're on your own when you use phase margin beyond that. Does that make sense?
Yes.
Yes.
Well, why do some people like to use the criteria that if the phase is a negative 180 degrees and the magnitude is greater than 1, it's unstable? Are they just using different words to say the same thing that we're saying here?
Well, first of all, I regret using the term stable or unstable. Why did I regret that? If you're worrying about whether an amplifier is stable or unstable, you've got a lousy amplifier. You need to be worrying about how close your angle of your poles are to about 60 degrees. So what you've talked about is a stability criterion. not typical compensation criteria. Okay, any other comments? Ben, how much time do we have left?
10 seconds.
So we'll also get the results from a more complete analysis. This analysis is based only on finding the poles, and we missed the zeros. How many seconds?
0.
That's all for today, thanks.
Thank you very much. We'll see you tomorrow.
Yeah, we'll see you tomorrow morning.